In this talk, I'm going to be focusing on the atmospheric meridional circulation. So that is the north-south component of the atmospheric circulation. And timescale-wise, the focus is on interannual to decadal timescales, and also a bit more on the large scale side, and not on the mesoscales, but you'll see that there's connection between the two scales. So I hope this is going to be interesting for other project members too. This work has received support from various sources, thanks to the FNRS, which is the Belgian funder of basic research, and the Belgian Science Policy Office, called the RESIST project I'm a collaborator on, and of course the EERIE project. I have the pleasure to share these results in collaboration with my colleagues from UC Louvain in Belgium, and also from the Nansen Environmental and Remote Sensing Center in Bergen, Norway, and from the University of Washington. So thanks to all these co-authors as well for providing this exciting opportunity. So Antarctic sea ice, as our understanding, it regulates the response of the global climate system to anthropogenic forcing. And this is really important because this happens via primarily the surface albedo, and also regulates oceanic carbon uptake, primary production, Antarctic bottom water formation, and thus through brine rejection, it impacts the world ocean circulation, the meridional overturning circulation, for example. And also Antarctic sea ice plays a role in, acts as a buffer kind of, and protects ice shelves from ocean swells. So Antarctic sea ice really has an important role in the climate system. However, the long-term changes in Antarctic sea ice has quite been a puzzle recently, because we have observed an expansion over the satellite era since 1979 up until 2016 or 17. However, since then, there's been a dramatic decline affecting all seasons, but primarily the summer and the winter seasons. And there is no existing mechanism yet to explain thoroughly both the oceanic and the atmospheric part, how the two forcings together can explain both the expansion and the following decline. So this talk and this research was primarily aimed at improving our understanding how the atmospheric circulation can act as a driver of both the expansion and the following decline. And I will also touch on an important topic, that is the question if there is a zonally symmetric response of Antarctic sea ice to climate change. I asked this question because, as we have seen, there are stark regional contrasts in the recent low ice events. For example, in 2023 winter, there has been quite large extent of Antarctic sea ice decline in the winter. However, that was a continuation of an ongoing trend in the Weddell and Bellingshausen seas. However, in the eastern part of the Southern Ocean, this was more like a drop. So in the long-term context, it's really an important question how Antarctic sea ice really responds as a zonally symmetric, if it produces a zonally symmetric response, or we should expect some meridional differences or non-zonal differences in the trends in the future. Changes in atmospheric circulation in the Southern Ocean are pretty well known to be linked with long-term sea ice changes. Regarding previous works, I like to separate previous works, and just to provide a very short introduction. So I separate works focusing on the summer versus the winter season. In summer, previous works primarily focused on the surface westerly changes that are associated with the southern annular mode. And these surface westerlies were shown to have strengthened in the summer. And this is in close connection with the eddy-driven jets response to CO2 forcing, which was shown to have not only shifted, but also increased in strength. And since westerlies carry excess momentum relative to the Earth's rotation, shifts in the latitudinal position of the jet will impact the poleward transport of momentum. And so this is basically described by the southern annular mode, as it is probably well known by everybody here. So the SAM, I like to see it as a rhythmic dance between the two jets merging and separating, and thereby influencing the momentum transport. And it's also important that the SAM has a sensitivity to the characteristics of the basic state. And in summer, the basic state is more zonal symmetric. However, in the winter season, climatologically, there is a strong low pressure system, the Amundsen Sea low, which causes kind of like a block in the zonal wind field. Therefore, the SAM will have a more non-annular component in the winter, and the meridional circulation anomalies can impact the circulation and sea ice in a more readily way in winter compared to as summer. Regarding the trends, in the summer season, there has been a trend in the SAM towards a positive phase. So the strengthening of the mid-latitude westerlies and also the surface westerlies. However, in the winter, the SAM's non-annular component was shown to have enhanced. So kind of like towards a more meridional mode. These were documented by previous papers. However, the cause for this change and the thorough understanding what's happening was not really shown yet. So my goal here is to understand these changes with a little bit of insights from eddy mean flow feedback and also stationary Rossby waves. So just to continue the introduction, I'd like to touch on just summarizing eddy mean flow feedback, just to be on the same page with everybody here. So let's see how interactions between the eddies and the mean flow can shape the meridional overturning circulation. So let's consider a quasi-equilibrium state of the zonal wind field, as the equation is shown here. According to this textbook equation, any non-zero value of the divergence of the eddy momentum flux, that is in the second term. So any divergence or non-zero divergence of eddy momentum flux will be compensated by zonal mean meridional wind. So, for example, pulvered heat transport by the eddies will be compensated by ADAB eddy cooling. So this will eventually alter the zonal wind field, so it changes the basic field, so that acts as a feedback onto the basic field. So there will be this feedback will happen. So it either feeds back or sustains or suppresses the eddy activity. So I'm sure everybody's familiar with these. So now let's take a look at the zonal wind climatology in the winter season at 200 hectopascals. So that is the jet stream level. This plot shows the zonal wind speeds, long-term average, that is the climatological zonal wind. The winter southern hemisphere exhibits a double jet structure with a dominant subtropical jet at all longitudes. The mid-latitude jet is confined to the Indian Ocean and it turns south in the Pacific while also weakening. This weakening is primarily due to the Amundsen Sea low, as mentioned before. So feedbacks between the eddies and the mean flow is confined primarily to the Indian Ocean, where both jets exist in the winter. However, the SAM in winter has a zonal varying component, which induces less zonal symmetry in the winter. So that is why that meridional circulation, we really have to study it to understand sea ice changes. And that's why I focused on this. And on the other hand, stationary waves also shape the mean state. The source of Rossby waves is determined by two components, the gradient of absolute vorticity and the divergent wind, as also shown in the title of the panel. The jet exit region over New Zealand will be an ideal location for Rossby wave source because there is the absolute vorticity gradient at the jet exit region. As I also shown the plot, the standard deviation of 200 hectopascal zonal wind with the contour, and with the shading I showed is the standard deviation of the Rossby wave source. So you can see that it's kind of overlaps with the subtropical jet exit region. So these two components will work together to produce a stationary Rossby wave according to Hoskins. And in the divergent wind component, we can also see that tropical sea surface temperature changes and the changes in convection can be associated with changes in the divergence wind in upper level. So these two sources can produce a stationary wave. So after this rather long introduction, I'd like to present my results. The first thing we did, we computed an MCA, which is a maximum covariance analysis that looks for patterns in two space-time data sets. And this will show us the the maximum covariance between two spatial fields. So in this term, V500, that is the meridional wind at 500 hectopascal, that is shown here, and the CS concentration. So in the first two plots, I show the leading mode of the maximum covariance analysis between V500 and sea ice. So this is a kind of like a zonal wave 3 pattern, as everybody would have expected. The associated time series, which is called basically a principal component time series for each mode, for each variables and each modes. This is only the first mode. It's shown here in the panel C. For the red, you can see the time series associated with sea ice, and the blue associated with the V500, that is the meridional wind at 500 hectopascal. This is monthly time series. If I compute an annual cycle and determine the trend in each month based on this data set, I find that there exists a trend in these time series basically only in May and June for V500 and in June and July for sea ice. So this time in the year, so May, June, July, seems to be something happening. So we primarily focus on these 3 months to understand why this trend can be happening. So there is a trend towards this mode and the associated sea ice pattern. So the first thing, we need to quantify what is the MCA-related sea ice anomalies. To do so, we can integrate the sea ice anomalies in this plot, and that way we get a number comparable to sea ice anomalies in observations. So that will be in million square kilometers. So the orange line here shows the MCA-related or the MCA-explained sea ice extent, that is only over the Bellingshausen Sea. So I restrict the sea ice extent calculations over the Bellingshausen Sea or the Weddell Sea. Or in the bottom, I show the pan-Antarctic, so the zonal mean, the total Antarctic sea ice extent. We can see that the MCA-related time series do a pretty good job in explaining the inter-annual variability and also the trend. Part of the trend is explained by the MCA. For the Bellingshausen and also for the Weddell Sea, we can see that not as much of a trend is explained in the Weddell Sea. However, it still it captures the significance of the trend. However, so there are 2 places, especially in West Antarctica, in the vicinity of the Antarctic Peninsula, where the MCA is doing a good job. So meridian winds can really play a big role. However, on the pan-Antarctic scale, the MCA shows a consistent expansion of sea ice, and it has very little sensitivity to capturing the recent drop in sea ice. So this was also interesting, and we try to understand why this happens. So as it's primarily related to the meridional mode, we will soon understand how the two comes together. So before we can correlate the time series of the MCA, so the principal components of the MCA, with other variables, for example, I show here the trended correlation between SST with a shading and Z200, that is a 200 hectopascal geopotential height, with the principal component corresponding to sea ice. So we can see this is known patterns. So connections with tropical Pacific sea surface temperatures, kind of like an in-phase connection with the Amundsen Sea and an out-of-phase connection in the Weddell and Bellingshausen Sea. And also the Z200 correlations show this standing wave coming from the tropical Pacific. So this is kind of like a Pacific South America pattern associated with the SAMS and its tropical influence. And if we do the same thing with other variables, I did ocean heat content in the upper 300 meters. We can see that in the Weddell Sea and also in the Amundsen Sea, there are 2 key regions that it's sensitive to meridional wind changes. And I also show downward long wave radiation and column integrated water vapor flux correlations with the principal component of sea ice. So basically the physical mechanism can be explained by local effects and remote effects. So the local effect is through thermodynamics. So this high pressure, whatever is positive correlation, this means high pressure over the Weddell Sea. Inside this high pressure, there will be descending motion, and the adiabatic warming of the air column will follow increased downward long wave radiation. So that is also can be seen that significant correlations with the downward long wave can be seen in the Weddell Sea. And plus the polar transport of water vapor is also key because that is the source of the long wave essentially. So not only the thermodynamics, but also the dynamic component of the transport of the wind is important. So basically negative sea ice anomalies are associated with enhanced downward long wave and enhanced water vapor flux. And this pattern is kind of like what we would expect. If we take a look at the trends, so the long-term trend-wise, the correlation map and the trend map pretty well matches. So there could be the same mechanism in the long term as it is in the internal timescales. So in here, I plot the sea surface temperature trend, which is also well known, and also the Z200 trend and the associated wave activity flux, the Rossby wave activity flux. We can see that really from the jet exit region over just the southeast tip of New Zealand, we can see the source of the Rossby wave, that is a standing wave coming from this region. And this is the trend in the Rossby wave source and the Rossby wave activity flux and the Z200 trend. So basically what we see is the Weddell Sea is well connected to the tropical Pacific. And the other thing we have to keep in mind is precipitation changes, because that is a well-known indicator of convection. As I mentioned before, convection is important for determining the upper level divergence. And what we see in the past 45 years regarding precipitation is kind of like an expansion of the tropical rainfall belt, especially over the West Pacific, so over the warm pool. The zonal mean precipitation trend in ERA 5 and the GPCP, which is an observational product or more close to observational product than ERA 5, is kind of like overlaps. So ERA 5 is quite trusty in terms of precipitation. And what we see relating to these sea surface temperature maps is the enhancement of the zonal gradient of SST in the Pacific, so cooling here and warming here. And the associated change in precipitation is also kind of like a shift towards a La Nina-like state. So that is more precipitation in the subtropics compared to El Nino years. So in La Nina years, we see more precipitation in the subtropics compared to El Nino years. This is a composite from this paper. So that the expansion of the tropical rainfall belt, and we know that it can induce changes in the zonal mean overturning circulation through the eddy mean flow feedbacks. So to better understand that, we also computed the trend in the southward eddy momentum transfer, which here is shown in this panel. So with the shading, I show the trend in the poleward eddy transport, and the contours show the climatological eddy transport. So we can see that there is a slight shift, but there is a significant strengthening of the poleward momentum transport over 35-ish longitudes in the zonal mean. And if I compute the latitudinal gradient, that is the momentum flux convergence or divergence, depending on sign, you can see that there is strong eddy momentum flux convergence at 35 south, which by mass continuity will induce upward convergence, so that downward motion will happen in the zonal mean because of mass continuity. And then vice versa, over 55 south, we see eddy momentum flux divergence, which will induce upward motion and surface cooling. And if we can see these trends in the zonal mean temperature and geopotential, I also show these plots. So this is the zonal mean temperature, and this is the zonal mean geopotential height trend. So the cause of the zonal oriented height rise at 35 south, which we can see here, this is a zonal oriented height rise basically. So in part is caused by changes in the eddy momentum flux, and it can be well seen in this geopotential height trend maps, and also some of the cooling associated probably with the Southern Ocean cooling can be explained through these changes in the eddies. So in short, the physical mechanism, what we discover is two components. I like to call it as a duet between the eddies and the tail connection. So the eddies work in the zonal mean, and the tail connection works in the zonal varying state. So this zonal mean perspective shows us that there is more subtropical precipitation. There's a trend towards more subtropical precipitation just because there is an expansion of the rainfall belt due to the change in the zonal SST gradient in the tropics. So there is larger warming in the West Pacific compared to the East Pacific, which will intensify the Walker circulation's upward branch. And that can be a source of changes in the mean state that will also affect the propagating eddies. So we know this from previous papers, but the linkages with sea ice were not as clear. So I create here a little sketch or a drawing to summarize key processes. So as step one, we have the strengthened tropical Pacific zonal SST gradient. Then here you can see the shading. With the shading is the SST trend, and the contours and the corresponding cylinders are referred to as the geopotential height trends. So warm colors mean geopotential height increase, so high pressure. So in step two, we have Walker circulation upward branch enhancement because of the SST gradient changes. So we have upper level divergence here, which is a good source of Rossby waves. And this overlaps, or kind of like in the same geographical location as the subtropical jet's exit region, where we also have the absolute vorticity gradient given. So the two things can work together to produce a stationary Rossby wave coming from the tropical Pacific and into the Weddell Sea, with a low pressure over the Amundsen Sea and a high pressure in the Weddell Sea. And these are also work in tandem with the zonal mean. So these high pressures will be intensified by the zonal mean changes due to the eddy mean flow interactions. And these low pressure centers can also be reinforced by the eddy mean flow, just because the adiabatic cooling that is appearing as a compensation of the change in the eddy momentum transport. So basically what I find is that we can have a new tug of war in Antarctic sea ice, basically CO2-driven eddy momentum flux convergence changes that we know from previous literature, so that the eddy momentum flux convergence changes are primarily driven by anthropogenic CO2. So this can cause Antarctic sea ice expansion, because we see that the eddy momentum flux changes will induce adiabatic cooling over the Southern Ocean, and that can contribute to Antarctic sea ice expansion. And on the other hand, CO2-driven ocean background warming can cause a circumpolar sea ice melt. So these two things can work against each other or even cancel each other. So this is kind of like a further complicated situation of the Southern Ocean, and we need to understand it better to better predict Antarctic sea ice. I also discussed that regarding the Walker circulation, there's been studies that climate models project a weakening of the Walker circulation eventually. That is against what is happening in observations currently, but eventually we expect that it will weaken. And in the present state, Weddell Sea warming and circumpolar cooling, it is favored by the Walker circulation intensification. So this can reverse in the future if that happens, or if this mechanism is robust. And so it would not be surprising to see overall a zonally varying rate of Antarctic sea ice response to global warming. So it's not just a simple zonal mean change. And I would especially like to see or hear comments about this tug of war. And yes, basically that's it. I just have some key references outlined here, and I would like to thank your attention.
Okay, thank you, Daniel. So there's a virtual round of applause I see going on. So thank you. So I guess we can have, we've got time for a few questions now before we move on to the next talk. So does anybody have any questions? Please, I guess, raise your hand. Thomas, I see you've raised your hand.
Yeah, thank you very much, Daniel. Very interesting presentation. I mean, so far, I think you have mostly analyzed observational data, right? And sort of EERIE is about modeling as well. And I'm wondering sort of what's your take on, before looking at modeling data, so how good the models are at doing certain things. And I would be particularly interested in this eddy momentum flux divergence. I mean, I think people have discussed before that going towards higher resolution, perhaps even kilometer scale, there may actually be some changes and some benefits to be had. Could you comment on that?
Yes. So yeah, that is right. So that is an excellent question because as we go in higher resolution, we expect to see better resolving of these eddies. However, these eddies are kind of large scale, so CMIP models already do a quite a good job in capturing these interactions. So for example, the strengthening of the eddy momentum flux, the polar transportive angular momentum in these kind of sense is pretty well modeled in the CMIP sense. So for example, I have taken a look at I have some additional slides from CMIP control runs. So I try to see whether in those control run years, so selected 45-year long periods where we have seen a decline in anorexic sea ice, and then I compare to those with a large trend in anorexic sea ice in the positive sense. So this is kind of like a composite between those years in the pre-industrial run when we have large sea ice drop versus where we have more sea ice expansion. And when I do a difference between those years, I also see this expansion of the rainfall belt, so more precipitation in the western part compared to less precipitation in the eastern part. So, and in the Z200, we see this standing wave and also the low pressure situated along the Southern Ocean. So basically with the zonal mean sea ice increase, models favor this pattern. So, but overall, yes, we should expect to see in high resolution better resolving of these eddies, but these are already pretty well resolved in the CMIP.
Thank you.
Okay, are there any more questions? No? In which case, this is good because it means we're running bang on time. We're halfway through the seminar and we've finished out with our first talk. And I guess on to our second talk now. So from Mukund Gupta, who, I guess I introduced him earlier. So do you want to share your slides and start when you're ready?
Can you see my slides okay?
Yes, we can see those. Okay.
Great.
Thank you.
Yes, well, first of all, thank you very much to all of you for attending and for Fraser for organizing and inviting me to talk at this meeting. So my name is Mukund Gupta and I work at the Delft University of Technology. And I was invited to talk today a bit about some work that I did a few years ago, which is on sea ice melt and how it can be influenced by ice-ocean interactions occurring at the ocean mesoscale. So I thought I'll start by showing a few observations. Here a sample of altimetry data that allows us to visualize some of the ocean currents that we have around the world. And this sort of map, as a lot of us will have seen before, helps us see the presence of these coherent vortices, what we call the mesoscale of the ocean. So they're particularly visible in the western boundary currents like the Gulf Stream, the Kuroshio, the Igulus Current. However, when we approach the polar regions, these sort of coherent features become less evident from this altimetry because the sort of radius of deformation of these eddies is expected to decline as we go towards the poles due to the beta effect, and also because the sea ice cover doesn't allow us to see what really is happening at the surface below the ice. However, in modeling studies, we do have some indication that the ocean is not quiescent underneath the sea ice and around the sea ice regions. This is some work by Meneghello et al. In 2021, who showed that there is indeed quite a bit of eddy activity in the ocean in the periphery of the ice, near the surface. And as we go deeper in the ice, deeper in the ocean, we see activity at depth as well, right below the sea ice cover. And so it's important to try and understand what the effect of these eddies might be on the sea ice cover and climatologically in general. So And some motivation for that is some work by Lee et al. In 2024, which used the Fraser model at fairly high resolutions to sort of estimate what might happen to the Arctic going forward in terms of its eddy activity. And so the top panels here represent quantities in the sort of modern Arctic in 2015 and 2095 in the bottom. You can see how the presence or not of sea ice can influence the amount of eddy activity that we see. So where we have a lot of sea ice, we see relatively quiet eddy activity, but as the ice retreats, then that activity strongly increases. And we want to understand how this transition might occur, if it does indeed, and what the effects of these eddies might be. So what we see in observations as well is that the polar regions are fairly interesting from an oceanography perspective because they are characterized often by a temperature inversion. That is, that there is typically cold and fresh water that underlies a warmer and saltier thermocline, and that layer can vary between several meters to several tens of meters, depending on the region. And so a question that has been on polar oceanographers' mind for a long time is whether some of that heat that is stored at depth can make its way up towards the sea ice cover, as there is enough heat in theory to melt a lot of the sea ice. And this work by Martinson and McKee in 2012 looked at some moorings in the western Antarctic Peninsula, and they noticed that there is periodic upheaval essentially of these of this thermocline layer, and that can bring some of that heat up towards the surface, and in some cases melt a bit of the ice. And this was also illustrated by the work by Ackley et al. In 2015 here in the Amundsen Sea, looking directly at ice-ocean heat fluxes via ice mass balance buoys. And they noted that even during the relatively cold months of October, we see oceanic vertical heat fluxes to the ice on the order of 10 to 20 watts per meter squared. So here, that motivated us to try and understand these vertical heat fluxes better. And so these were the questions that we had. So we wanted to see whether mesoscale eddies indeed have an influence in fluxing heat towards the mixed layer. And also then understanding whether there is a net effect from that eddying heat flux on global sea ice melt throughout the seasonal cycle. So we took a relatively idealized approach in our work. So we considered an idealized model of the Southern Ocean. So this is a channel model based on the MIT-GCM beta plane. So it has coupled sea ice and ocean dynamics, and it is forced by atmospheric conditions taken from the core data set at 30 east. So this is just right below the tip of South Africa. And the model is zonally reentrant. So in this direction over here, it's symmetric. And there is a southern boundary over here, a northern boundary over here, which acts as a sponge layer. And the model has a 4-kilometer resolution. So it's eddy resolving in its northern parts and becomes more eddy permitting, if at all, as we approach the sea ice covered regions and the shelf. So we ran this model up to a quasi-equilibrium state for a few hundred years. And the model then equilibrated to these quantities essentially. So we have the potential temperature distribution on the left with the temperature inversion that we were considering before in the observations right below the sea ice. So we have this cold and fresh tongue of water over here right below the sea ice, overlaying the warmer waters coming from below here. And this warmer water is also saltier, and it's being entrained by the overturning circulation in its clockwise branch over here and the anti-clockwise branch down below. So this represented a relatively realistic state compared to the observations, although of course still idealized, but something for us to think about processes. So we went ahead and tried to think a bit about what the temperature and vertical heat fluxes were doing in this model, particularly near the surface. So here I'm just going to show you a movie where we have the sea surface temperature anomaly at the top relative to the zonal mean. And at the bottom, we have the vertical velocities right below the surface. And I'm going to go through each month, so for 1 full year. And you'll see this dotted line over here move around because it represents the mean sea ice edge. So let me just start it. So we start in January, which is around the summertime, and we have relatively contracted sea ice, and then we expand until, let me just pause it here. This is the month of August, and we have this expanded sea ice cover. And what we note over here is the presence of these hotspots in the temperature right below the sea ice cover over here. And associated with these hotspots, we had relatively enhanced vertical velocities when we look at the bottom panel. And this continues essentially till the months of September, October, until we retract back and come back to the starting position. So we were quite interested in what these hotspots meant and if they had any influence on the melting of the pack. So we just had a hypothesis that perhaps what was going on was the fact that as the ice expands and becomes relatively compacted, then that ice essentially acts as a source of friction for the eddies that are underneath. And so if we think of the ice as being relatively immobile compared to these eddies at those scales, then for anticyclones, anticyclones are going to experience Ekman suction. So that might be a cause for bringing these warmer waters up to the surface, whereas cyclones will experience Ekman pumping, and so vertical velocities enhanced in the downward direction. So that's kind of what we thought as a first order mechanism, and we wanted to see if there was any evidence for it. So the first thing we did was to evaluate what the Ekman pumping and suction velocities were, and just visually compared them with the diagnosed vertical velocities. And we saw that there is indeed quite a bit of pattern correspondence between the two, particularly given at the larger scales, and particularly when we think about where these patterns occur, that is where the ice is most concentrated. So where the ice concentration was above 80% or so, there was a good correspondence between these two, but in the looser pack, then the Ekman velocities just disappear. And so there are other mechanisms, of course, contributing to these vertical velocities. We have Rossby number on the order of 0.5 or up to 0.5, and so there are nonlinearities also contributing to those vertical velocities, but we wanted to focus on the linear mechanism first. So in order to assess the sort of quantitative behavior and the quantitative effect of this Ekman pumping, we designed another simulation where we tried to turn that effect off. And so just to give you a visual impression of that, we have the full simulation on the top, where if we look at the stress in the y direction, we see a lot of these small scale patterns at the mesoscale. And so we wanted to design a simulation which has the same mean stress, but essentially without the variations that we're seeing over here. So this is what we did in this EIP off. So we just had to calibrate the simulation such that in the zonal mean, the stress is relatively similar between the two. So instead of having contributions from both the atmosphere and the ocean, we just use the atmospheric component with a scaled factor. So then the other thing we wanted to do was to look at the individual eddies themselves. So we defined two different regions, one which was always in the open ocean and one which was always underneath sea ice. And essentially detected some eddies using a fairly standard method based on sea surface height anomalies. So we detected essentially peaks in the sea surface height anomaly field and applied some criterion. So the contours around it had to be of a certain shape and minimum number of pixels, etc. And those forms are cyclones and anticyclones, respectively. So this is what we obtained when we look at these composites. So the horizontal axis over here is normalized and then rescaled to the mean radius that we were seeing. And this is for cyclones, and on the right we have the anticyclones. And those are just underneath the sea ice. So if you want more information, the paper has both the sea ice and the open ocean versions. But essentially what we're seeing is that the cyclones tend to be relatively cold all the way through and very close to the freezing temperature. So there were sites of sea ice formation. And this, I forgot to mention, was during the month of September mostly. And in anticyclones, on the other hand, we had this warmer water. And so this was a site where sea ice tended to melt mostly. And then we compared what happened between the simulations that had the full mechanism on versus the one that didn't have it. And we looked at the vertical velocities, again, in composite form. And what we see is that the sort of full lines are always bigger in magnitude than the dashed lines. So essentially, when we have the mechanism on, we have larger vertical velocities in magnitude. So cyclones have stronger, stronger upward vertical velocities, and cyclones have stronger downward ones. On the other hand, when we look at the surface, sea surface temperature, we don't see the same patterns between cyclones and anticyclones. So the anticyclones are indeed warmer when we turn the mechanism on, but that's not the case for the cyclones, which remain at this freezing temperature or close to it. And therefore, we see that we might expect a rectified effect because basically the mechanism is not symmetric between the two. And that's indeed what we see. So the melt that we're seeing in anticyclones is stronger than the increased freezing that we see in the cyclones. And so if we look at sort of now integrated quantities over a full region, this is the heat flux budget essentially with contributions from the eddy, the mean, and the total, and its effect on the melting and freezing of the ice. This is what happens in the mean state. But now if we take the difference between EIP on minus off, then we see that the eddy component is strongly increased. And so there's during the seasonal cycle, in particular between June to October, we see an enhanced heat flux towards sea ice. And that leads to a diminishing of the sea ice thickness by about 10 to 15 centimeters over the course of this first year. And so we wanted to see if that effect accumulates over the years or not. And the short answer is that it doesn't. So there is, when we look at the surface temperature, the temperature profile, then there is enhanced heat flux during these winter and spring months. But then this tends to basically create more sea ice melt, which stabilizes the column, and then the effect then just reverses for the rest of the seasonal cycle. So basically we have kind of this seesaw happening, and the effect is mostly in changing the seasonality of the sea ice cover and the upper ocean properties, rather than creating a long-term trend. And we see this also affecting, as we said before, the sea ice thickness. So that's the blue line over here. So the first year sees that decline, then it recovers due to the freshening of the waters, and then we see the decline again due to the eddies, and that cycle continuing back and forth. And we also see an effect on the mixed layer depth. So again, that tends to shoal by up to 60% due to the extra sea ice melt, but then deepens up again the following season due to increased sea ice formation. And finally, we do see effects on the atmosphere and ocean heat fluxes as well. So some of the heat that was upwelled, not all of it goes towards melting the ice, but some of it actually warms the atmosphere. And again, that follows a seasonal cycle. So of course, the model that we have is not coupled. So it would be interesting to see whether having a coupled model would change this story or not. Yeah, so just a few conclusions. So we saw that in winter and spring, we have a mechanism due to Ekman pumping, which enhances vertical velocities underneath the sea ice cover, as the ice is relatively stationary compared to the scale of eddies. That leads to upward enhanced heat fluxes under under anticyclones, but that is not compensated by cyclones because they remain at the freezing temperature. And this leads to 10 to 15% sea ice loss during those spring seasons, and shallower mixed layer depth by up to 60%, which then recovers throughout the rest of the seasonal cycle. So you can read more about this in our paper in JGR in 2020. And maybe just wanted to give a slight perspective on some outlook, some things that we've been working on since then. So this work that I just presented was focusing mostly on highly concentrated regions of sea ice, 80% or more. But of course, when we look at imagery, we see a lot of presence of eddies at the edge of the sea ice pack or the marginal ice zone. See sort of this picture of broken up sea ice pieces or flows. And so we were quite interested in understanding how these individual pieces interact with the eddying currents. So we've been thinking a bit about discrete element models and understanding things happening at even finer time and spatial scales. So if you're interested, definitely feel free to reach out. So thanks a lot, and happy to take questions.
Okay, thank you very much for a fascinating talk. I can see there's again a virtual round of applause going on. So yeah, please raise your hand if you have any questions for Mukund. So I have a question actually. So the eddy ice pumping mechanism you were talking about, so it's asymmetric, and so it tends to lead to thinner sea ice when we have the eddies present. Does this mean that we have to think? So I guess when we're running eddy resolving models, we've brought with us the sea ice models and sea ice parameterizations from coarser resolution models. Do we need to rethink how we treat those and how we approach kind of tuning those models because of this asymmetry, do you think? Or do we just have to choose new parameters in the parameterizations or in terms of the tuning, or do we need to, do we need a bigger rethink about how they work?
Yeah, that's a good question. The principal source of the asymmetry is in the thermodynamics. It's mainly due to the fact that you can't get sea ice being colder than the freezing temperature, or water being colder than the freezing temperature. So this is something that should be captured by the current thermodynamic formulations. Now the question is whether we have enough high resolution to capture the vertical velocities and their location with respect to the temperature and salinity anomalies, because that turns out to be quite important, where these anomalies are co-located with each other. One of the things that we've been thinking about a little bit in terms of parameterization is this effect of restratification by submesoscale eddies right near the surface. Those tend to happen at submesoscales, and even with high resolution models, it's usually quite hard to capture those. And there's some indication that the current parameterizations for the open ocean might not be appropriate for underneath sea ice.
Okay, thank you. Matthias, I see you have your...
Yes, can you hear me?
Yes.
Okay, so I readily understand the asymmetry for the cyclones and anticyclones, but you showed that there's no long-term trend. There's just a moving of the climatology. What is the asymmetry? How can I understand the asymmetry, the compensating asymmetry later on, so that we don't have a trend?
Yeah. There are two things happening here. So one is the asymmetry is indeed causing more melt during the spring and winter seasons. And then it's being compensated later on in the seasonal cycle. So the compensation is perhaps what you're asking about.
Exactly.
So we believe, at least in the model that we have, that it's mostly due to the stratification feedback. So as we are able to melt more sea ice, then we stratify the upper ocean, which leads to a more easily cooling of the surface, because it's the mixed layer depth is shallower. So that favors conditions for enhanced freezing later on in the year. And so we have the sea ice then recover in its thickness.
Okay. Thanks.
Are there any more questions? No. In which case, I'd like to say thank you very much.
Steffi has a friend.
Oh, does she? Yes, I see that. Steffi, go ahead.
Okay, so I have a question, because the EIP mechanism, it's based on the friction between the ice and the ocean eddy, and so there is the dynamics of that. But there's also the dynamic effect of the eddy that converges or diverges sea ice, right? So like how that must be it is usually compensating in the opposite way, right? So in an anticyclone it converges or something. So like how can we sort of think about the total effect in that way, separating the dynamic in it and thermodynamic effect of the eddy?
Yeah, good question. I don't have an immediate answer quantitatively. Here we were thinking about regions that were relatively compact in sea ice, and so the dynamic effect of the eddies converging or diverging sea ice, at least from what I can say without looking at our computations, was relatively minor compared to the effect that we're seeing from the thermodynamics. I would expect the effect to be stronger in marginal ice zones where you have enough space for that convergence and divergence to occur.
Thank you.
Okay, and I see we have another question from Vasco Muller.
Yeah, thanks for the talk. Sorry about that. Just a very quick one, I guess we're nearing the end. So about the sea ice model, and you showed at the very end in your outlook about the marginal ice zone and eddies moving ice from the more compact to the open ocean side and vice versa. And I was wondering if you can speculate about what would happen if we go towards moving more discrete ice models. Instead of thinking in terms of sea ice concentrations, and if we go into a more either there is ice or there is no ice as it is in the real world, right? And how that would affect things.
Yeah, that's essentially been a big theme in what we've been thinking about. Some of the effects that we're seeing is that if we account for the size distribution of these individual size of flows, then the melt rates are affected. So basically, we find that smaller flows tend to melt faster than bigger ones. So if we have the same concentration but distributed over different sizes, that can change the melt rate of the overall pack by several days. We're seeing also effects in the rheology. So the friction between the ice pieces will depend on their shapes and their sizes. So we have some things that show that finer pieces will behave a lot more like a continuum as we expect, but the more bigger pieces you have, the more you have to think about their individual effects and potential blocking effects. And so we're seeing in different characteristics, whether it's the rheology, the melt, or interactions with eddies, some effects there. So yeah, we're kind of curious about thinking how we could integrate these into the future climate models.
Thank you. Thank you.
Okay, well, I'm not seeing any more hands, so I guess this time we will thank both our speakers for some really interesting talks about how sea ice is interacting with the mesoscale of the atmosphere and also the mesoscale of the ocean. The eagle-eyed amongst you may have noticed that my background has changed. And this is behind me. You should be able to see the advertisement for next month's Science Hour, which is on the 17th of March. And at this Science Hour, we have two talks, both from the Met Office. One from Michael Lai, who is an early career researcher who is who's been looking at how different experimental protocols affect control and historical simulations. And then we also have a second talk from Malcolm Roberts, who's going to be talking to us about the eddy-rich pre-industrial control simulation that the Met Office have been running and comparing that with lower resolution models. So yeah, that's the 17th of March at 2 o'clock. So please put that in your calendars and please do come along. Until then, I think that's it. So thank you everyone for coming. And yeah, I look forward to seeing you all again in a month.